All right, on this slide, we're going to do a sample problem involving the dissociation constant of a weak acid as well as that activity coefficient that we obtained using the Debye-Huckel theory. Okay, so here's our problem. Acetic acid has a dissociation constant equal to 1.75 times 10 to the negative fifth moles per kilogram. Calculate this gamma plus minus and degree of dissociation for a 0.45 mole per kilogram solution of acetic acid. Okay, so there's a number of things that we want to lay out before we begin the problem. We will assume that this gamma plus minus equals 1 just to start out with. We're going to adjust it over time as we do the problem. I'm going to assign the variable x to be the molality of the protons, which also happens to be the molality of the anion for this acid. Okay? And this molality of HA, at least starting, is going to equal 0.45. And then later on, as the acids dissociate in our calculation, then X molality of those will disappear. So we have minus X. So the way we set up this problem is that the dissociation constant is going to equal this gamma plus minus squared. Then we'll have the molality of H plus, molality of A minus, over the molality of the non-dissociated acid. So now let's enter in all of our known numbers and variables. We've got 0.175 times 10 to the negative fifth. And I'm just going to be a little bit relaxed with units on this problem because it's just going to get too troublesome otherwise. I'll just need to be careful and tread carefully from this point forward. So this is going to equal just 1 squared, because I'm starting by assuming this gamma plus minus is 1, multiplied times x squared over 0.45 minus x. But this will approximately equal x squared over 0.45. Why is that? Because here we know that this dissociation constant is so small, which means that the reactants are going to be heavily favored, or this HA will be heavily favored. Okay? So step number 1, assuming that this activity coefficient equals 1, if you rearrange this stuff all algebraically, you get x squared equals 0.75 times 10 to the fifth times 0.45. And then you solve for that by multiplying those and taking the square root. You get x equals 2.806 times 10 to the negative third. And this is the molality of our protons. Now the next step is we'll want to calculate the ionic strength, because that's what's going to give us our first estimate of that activity coefficient. Nu plus z plus squared plus nu minus z minus squared. And then plugging in all those numbers, our m, which is the molality of the solute, which is going to be the molality of the solute that's dissolved, is just this number up here, 2.806 times 10 to the negative third, divided by 2. And then inside here we get 1 times 1 plus 1 times negative 1. Oops, I'm forgetting to square that and that. And this just equals 2.806 times 10 to the negative 3 for our ionic strength. Now we are going to calculate our gamma plus minus using the Debye-Huckel theory of electrolytes. This is going to be E raised to the power of negative 1.173 times the absolute value of 1 times negative 1 times the square root of 2.806 times 10 to the negative 3. Plugging this into your calculator, I forgot an equal sign there, your gamma plus minus is going to be equal to the exponent negative 0.0621, which is just 0.9398. Don't forget that exponent of something is just e to the power of that something. This is going to be our estimate of that gamma plus minus for our next step. So now we get to step 2. We'll iterate, meaning just do the same thing over again, with a new gamma plus minus. So now when we arrange our algebraic equation, we'll get Ka equals this gamma plus minus squared, x squared, over 0.45 minus x. And we're going to plug in our old value for x into there, but then solve for this x squared. So let's go ahead and enter that. That means that 1.75 times 10 to the negative fifth equals this gamma plus minus squared. So I square this value here. That equals 0.8831 times x squared, and then 0.45 minus 2.806 times 10 to the negative 3. So once I solve for that algebraically, then this is going to equal 1.75 times 10 to the negative fifth, and then over here 0.45 minus 2.806 times 10 to the negative 3. And this is all over 0.8831. Now when you solve for that, you should get x equals 2.976 times 10 to the negative 3. And this is the molality of RH+. Okay, let's calculate the ionic strength. 2.976 times 10 to the negative 3 divided by 2. And again, we get 1 times 1 squared plus 1 times negative 1 squared. And this just gives us the concentration as the ionic strength back again. And our gamma plus minus equals e to the power of negative 1.173 times the square root of that ionic strength, 2.976 times 10 to the negative 3. Okay. Which gives us a new activity coefficient of 0.9381. Okay, so then step 3 of this whole process is just repeat until converged. And you may have to do this several times, but we're going to do it just one more time. So now we solve for x squared again, which is going to be just this Ka, and then 0.45 minus the concentration that we got on the previous step, 976 times 10 to the negative 3. And then this is divided by our new gamma squared plus minus. So that's going to be 1.75 times 10 to the negative fifth, 0.45 minus 2.976 times 10 to the negative 3. And that's all over 0.8780. And that's going to give us an x, once we take the square root, of 2.98 times 10 to the negative 3 moles per kilogram for that molality. Nice. And that is going to be our, that is converged enough, I would say. It's very similar to the previous concentration that we got, so I think that is converged sufficiently. So now, lastly, we need to find the degree of dissociation. And the degree of dissociation is going to be the molality of H plus divided by the original molality of the HA, okay, times 100%. So this, we just plug in 2.98 times 10 to the negative third there, and we plug in 0.45 right there times 100%, and the result we get once we plug that into our calculator is 0.6%, so less than 1% of this acid is dissociating. Now, I remember learning about weak acids in general chemistry, and I remember wondering, well, what percentage of the weak acids are dissociating in solution? And here's your answer. It looks like, at least for acetic acid, it's less than 1%.